Hello, and welcome to our video on norms. In the broadest sense, a norm on a vector space X is a way of measuring the length of vectors in X. Let's start with some hopefully familiar finite dimensional examples. We'll take X to be Cn or Rn. These are all n tuples of real or complex numbers. So if I have a vector X, which I'll always write as bold X in Cn, then X is equal to the ordered n tuple x1 through xn, where each xk is a complex number. And everything I say here would also work for the real numbers, but we will enjoy complex vector spaces a little more in this class, so that's why I'm posing everything in C. And we'll study a few norms in this X equals Cn in detail and learn a few of their properties, and then we'll generalize that to the broader definition of what a norm is, and last we'll look at a few other useful norms that we'll meet in our class. Maybe the most famous norm that you know on Cn is the 2 norm. So the 2 norm of X is the square root of the sum from k equals 1 to n of the modulus of each xk squared. And this gives Euclidean distance. If we're working in R3, this is what we think of as the linear distance between 2 points in R3. Another very useful norm is the infinity norm. So X infinity norm is the maximum of the moduli of xk, where k, of course, goes from 1 to n. And we call this, unsurprisingly, the max norm. And then more generally, we have a p norm. So norm xp will be the 1 over pth power of the sum from k equals 1 to n of the modulus of xk raised to the power p. And this is for any p between 1, including 1, and up to but not including infinity. So certainly the 2 norm is one of these p norms. And here are some common properties of these functions, norm p, and we'll do the proofs for p equals 1. So all of these norm p's take in vectors x and cn, and they spit out real numbers. They're maps from Cn to the reals. First, the p norm is always non-negative. And we're going to do this, of course, for p equals 1. So in p equals 1, we'll look at the sum from k equals 1 to n of modulus of xk raised to the power 1, and then that whole sum raised to the power 1 over 1. So that's the sum from k equals 1 to n of the modulus of xk, and that is certainly greater than or equal to 0, because each modulus of xk is non-negative. You add a bunch of non-negative things together, you get something non-negative. Second, the p norm is equal to 0 if and only if x is equal to 0. So let's look at the 1 norm of the 0 vector. This is the sum from k equals 1 to n of the modulus of 0. Just adding a bunch of zeros, I get 0. On the other hand, suppose that the 1 norm of some vector x equals 0. We want to show now that x is the 0 vector. So this tells us that the sum from k equals 1 to n of the modulus of xk is equal to 0. Suppose, by contradiction, that xj is non-zero for some j. What does this tell us? Then 0 is strictly less than the modulus of xj, which is less than or equal to the sum of all the moduli, sum from k equals 1 to n of modulus of xk, and that has to be equal to the 1 norm of x. So I started out with the 1 norm of x being 0, and now I have the 1 norm of x being greater than 0. That can't happen. Third, the p norm of alpha times x is the modulus of alpha times the p norm of x for all scalars alpha. Let's calculate this out. The 1 norm of alpha times x is the sum from k equals 1 to n of the modulus of alpha times xk. This is the sum from k equals 1 to n of the modulus of alpha times the modulus of xk. Just split up that product. Now alpha doesn't depend on k, so I'll pull it out of the sum. This is modulus of alpha times the sum from k equals 1 to n modulus of xk. And that's, of course, modulus of alpha times the 1 norm of x. Fourth, we have the triangle inequality. The p-norm of x plus y is less than or equal to the p-norm of x plus the p-norm of y. To prove this, at least in the case p equals 1, we'll need to remember the triangle inequality in the complex plane. If z and w are complex numbers, then the modulus of z plus w is less than or equal to the modulus of z plus the modulus of w. So do this in the 1 norm. Norm of x plus y is the sum from k equals 1 to n of the modulus of xk plus yk. Now for each of those k's, I'll use the triangle inequality in C. This is the sum from k equals less than or equal to the sum from k equals 1 to n of modulus of xk plus modulus of yk. I'll just split that sum into 2 sums. This is the sum from k equals 1 to n of the modulus of xk plus the sum from k equals 1 to n of the modulus of yk. And that's the 1 norm of x plus the 1 norm of y. So these are 4 critical properties of all the p-norms, which we have proved for p equals 1. They extend for p greater than 1. They're even true for p equals infinity. So now we'll say that a norm on a vector space x over the complex plane is a map. I'm going to call it double bar dot double bar. I'm always going to pronounce that simple as norm. It's a map norm from x into the reals such that 1, the norm of f is greater than or equal to 0 for all vectors f and x. This is the positivity property. 2, the norm of f is equal to 0 if and only if f is equal to the 0 vector. Sometimes this is called definiteness. 3, the norm of alpha times f is equal to the modulus of alpha times the norm of f for all scalars alpha. And 4, the norm of f plus g is less than or equal to the norm of f plus the norm of g for all vectors f and g in x. And this is the triangle inequality. Now, if we have a map from x into the reals that satisfies property 1, the positivity, property 3 for scalar multiplication, and property 4, the triangle inequality, and if this map is always non-negative, but maybe for some f this map produces 0 even when f is not 0, then we call this map a seminorm. It should not be an f as a seminorm, it should be the map as a seminorm. So what is a seminorm? A seminorm is a norm, except it can produce 0 for a non-zero vector. Let's look at a few examples. Say we take x to be the vector space of all continuous functions on the interval a to b. Then we can define the LP norm. So for p greater than or equal to 1 and less than infinity, we'll put norm f LP is the 1 over pth power of the integral from a to b of the modulus of f of x raised to the power p. This is, I hope this looks a lot like the p-norm on Cn. It's sort of a continuous analog of the p-norm on Cn. And we can check some properties of this norm pretty quickly. So first of all, the LP norm has to be greater than or equal to 0 because the integrand is a non-negative function, and integrals of non-negative functions produce non-negative numbers. The scalar multiplication property is straightforward. If alpha is a complex number, then alpha times f in the LP norm is the integral from a to b of alpha times f of x raised to the power p, and then that whole integral raised to the power 1 over p. So in the integrand, I'll pop out a factor of modulus of alpha to the p, and then I'll pull that out of the integral, because I can always pull scalars out of my integral. And now I have this modulus of alpha to the p times the integral, whole thing raised to the power 1 over p. And here's where the power 1 over p is so nice, because it knocks out that power p on alpha, so I just get modulus of alpha times the integral raised to the power 1 over p, and that's modulus of alpha times the norm of f. The triangle inequality for this LP norm is rather harder to prove for p not equal to 1. Not impossible, just messier. So let's just do it for p equals 1. The L1 norm of f plus g is the integral from a to b of the modulus of f plus g. By the triangle inequality for real numbers, and by the monotonicity of the Riemann integral for real-valued functions, I know that modulus of f plus g is less than or equal to modulus of f plus modulus of g. So integral of modulus of f plus g is less than or equal to integral of modulus f plus modulus g. By linearity of the integral, that's integral of modulus of f plus integral modulus of g. And so that's the L1 norm of f plus the L1 norm of g. As for positivity, I want to be able to say that if the LP norm of f is equal to 0, then f has to be 0. That is, f is the 0 function, f of x equals 0 for all x. So how do we get this? Suppose the LP norm of f is equal to 0. That means that the 1 over pth power of the integral from a to b of modulus of f of x raised to the power p is 0. So we'll take the pth power of this integral. So the integral from a to b of f of x modulus f of x to the power p is equal to 0 to the p, which is 0. And now we need a calculus fact. If we have a continuous function on the interval a to b, and call this function g, and if g of x is greater than or equal to 0 for all x in the interval a to b, and if the integral from a to b of g of x is equal to 0, then it also turns out that g of x must be equal to 0 for all x in the interval a to b. And so if we believe this calculus fact, we see that f is continuous. That means that the modulus of f raised to the power p is continuous. In particular, p is a number greater than or equal to 1, so I have no division here, no division by 0 maybe. This means that modulus of f of x raised to the power p is 0 for all x in the interval a to b, because I have my calculus fact, and I've shown that the integral from a to b of modulus f of x raised to the power p is always 0. That's the power of calculus. Another norm that we can use is the following infinity norm. So if we continue to work on the vector space x equals the continuous functions on a to b, all of these continuous functions have maxima. This is just the extreme value theorem on a closed bounded interval for a continuous function. So I can define norm f infinity to be the maximum of the modulus of f of x over the interval a to b, and this also turns out to be a norm. And you can prove that in an exercise. Let's move to a larger space now than just the continuous functions on a to b. Let's take x to be r of a to b, which will be the Riemann integrable functions on a to b. So every continuous function we know is Riemann integrable, but there are plenty of Riemann integrable functions that are not continuous. They're discontinuous at 1 or 2 or 50 or maybe countably many points. That's possible. One calculus fact that we need is that if f is Riemann integrable on the interval a to b, then so is the modulus of f raised to the power p for any p greater than 0. So this means that the maps norm fp are all defined for 1 less than or equal to p less than infinity. And it also turns out that if f is Riemann integrable on the interval a to b, then f must be bounded, so its infinity norm is also defined. Now, are these things all norms on the Riemann integrable functions? Well, basically all the properties that we showed for the LP norm on the continuous functions can be proved in exactly the same way if you have a Riemann integrable function. What did we use in those proofs? Really just the linearity of the integral to pop out a scalar, or to say the integral of a sum is the sum of the integrals. The only time that we explicitly used continuity was in talking about the positivity property, or the definiteness property. And here's where it's going to break. Say I define my function f0 of x to be 1 at x equals a, and 0 for x greater than a or less than or equal to b. So clearly f0 is discontinuous at x equals a because it jumps from being 0 to 1 there, and otherwise it's continuous on the interval open at a, closed at b. This means that f is going to be a Riemann integrable function. It's a piecewise continuous function. And you can calculate that the integral from a to b of the modulus of f0 of x raised to the power p, well, that's really just the integral from a to b of 0, and that's 0. And why do we have this equality of the integrals here? Because f0 is identically constant on the interval open at a, closed at b, and it just changes value at this one point x equals a. So calculus tells us that the integral from a to b of modulus f of 0 of x to the power p just agrees with the integral of 0. Changing the value of f at that one point x equals a doesn't change the integral. But clearly f0 is not the 0 function, because we've defined it to be 1 at x equals a. It's almost the 0 function, except for that one point. So these p-norms, these LP norms, are only semi-norms on the space of Riemann integrable functions, because you can find functions that are non-zero, and yet the LP norm of that function is 0. So here's the uncomfortable fact. If you have a semi-norm, then the semi-norm at a vector f equals 0 does not mean that the vector f equals 0. It's like saying, yeah, something has 0 length, but it's not 0. I mean, imagine if you had a point x in the reals with the modulus or absolute value of x equals 0, but x was not 0. That just could never happen. This is one of the more uncomfortable features about seminorms, in particular, seminorms involving integrals and integrable functions that aren't necessarily continuous.